Good morning, everyone. I'm Shannon Wetzel, Managing Editor for Metal Casting Design and Purchasing. Welcome to today's webinar, High Performance Aluminum Casting Alloys for Engine Applications. Today's speaker is Mr. David Weiss, Vice President of Engineering and R&D for Eck Industries, Inc. He is responsible for development and application of high-performance alloys and casting concepts for the foundry and its customers. Weiss has authored over 50 papers on the processing and application of aluminum, metal matrix composite, and magnesium castings, and in 2015 he received the John A. Penton Gold Medal from the American Foundry Society for pioneering work in the premium aluminum casting industry. Now, before I hand it off to David, I want to go over just a few general things about today's webinar. The webinar will be recorded and made available to today's attendees. You will receive an email with a link to the recording within a week after the webinar, so look for that. And then secondly, David will be answering questions at the end of the session, and you can type the questions in at any time during the webinar, and we'll address them at the end. And you can use the question box in your control panel there to your right. So without further ado, I will hand the control over to David. And thanks again for joining us. David, I believe you might have muted your phone.
Thank you very much. Good morning, everybody. I'm pleased to be able to present this webinar to everyone this morning. The team that was working in this development is shown. We had a number of individuals from 3 national labs that worked along with us on this program. We're the industrial partner on the program. This is work that was sponsored by the U.S. Department of Energy through the Critical Materials Institute. And the primary function of the Critical Materials Institute is to be able to make sure that we have an adequate supply of rare earth elements for our industrial and research needs, including things like magnets and phosphors and a number of other things that are very, very important to our economy. And they do that through multiple programs that are looking to recycle, substitute, or reduce the use of rare earths in applications where they're currently in. So you should ask the question, well, if they want to reduce the use of rare earths, why are we talking about an aluminum alloy with a fair amount of rare earths in? Well, the rare earths that we're talking about, or the rare earth that we're talking about, is cerium. And interestingly enough, cerium in most rare earth deposits represents about 50% of the rare earth oxide that is in those deposits. Cerium does not have many industrial uses. There's some of it used in polishing compounds and some of it used in some minor applications. But most of the cerium that gets dug out of the ground after the other important rare earths are pulled from it gets dumped back in a hole in the ground, and so it is really not used. And so the ability to use cerium reduces the cost of operating of extracting the other rare earths, and gives these mines another revenue stream, which should help to stabilize supply and reduce cost of some of the rarer rare earths. When you talk about adding rare earths to an alloy, sometimes there's a concern about, well, that's just going to be too costly to use. That really is not the case. Cerium converted from the ceria ore, cerium as a metal, is priced at about $2 a pound. And so when you look at adding that material in some small percentage, 8 or 10% into an alloy, the premium over commercial alloys is modest if it's there at all. With some alloys that contain a lot of copper, depending upon what the copper metal market is, the cerium can be cheaper than the copper that's put into an alloy. And if there is a penetration into the transportation market, it doesn't take much of a penetration to use substantial amounts of cerium, and therefore meeting the goal of the Critical Material Institute as far as stabilizing supplies of the material. So that's a little bit of the background. We know a couple things about cerium. Some of this is known from some very small research studies, and some of this was developed through some work that was done in powder metallurgy some 30 years ago. When you mix aluminum and cerium, you get a highly stable intermetallic, Al11Ce3. It's a highly stable intermetallic. And the breakdown of that intermetallic does not begin till about 1,000 degrees C. So it's very, very stable at high temperature. The intermetallic is very stable at high temperature. The intermetallic phase is resistant to coarsening. And what we're really trying to say is that cerium has no real solubility in the aluminum, in the aluminum phase, and so it's got nowhere to go, and so it's thermodynamically trapped. The original research was in powder metallurgy, and the powder metallurgical results point to a possibility of fairly high tensile strengths up to about 230 degrees C. So it seemed like a possible application for a cast alloy. Here we see some of the original microstructures that were done, and you should be able to see the various scale bars on there. What we have is a very, very small aluminum-cerium phase. When looked on edge, the rods are about 100 nanometers in diameter. When you add cerium in percentages of between 8 and 10%, you have a very, very high phase fraction of cerium in the material. The microstructure is interconnected. If you put too little cerium in the alloy, the microstructure doesn't connect very well, and so you have denuded areas, but typically above about 7% cerium, that does not happen. And really you have sub-micron scale laths that define the shape of that intermetallic. And so part of what we were trying to do is develop a cast alloy that had high temperature properties, and was affordable and was castable. In the lower left-hand side, you see the relative intermetallic content of some of the other alloys that are out there. These alloys do not have unusual amounts of intermetallics, but the intermetallics that are there are much more stable. So here's a TEM picture showing a little better that this microstructure is primarily an aluminum-cerium phase in in an aluminum alloy. And you get an idea of the size. That's a 1,000 nanometer scale bar on the bottom, and pretty uniformly distributed through the alloy. There's not a lot of phase diagram information, although Mundolfo did some years ago that we believe it turned out to be fairly accurate. This is a computed phase diagram done by the folks at Lawrence Livermore, and we see a lower melting eutectic point at about 10% cerium. That really gave us some hope that we would have an alloy that you could get a substantial amount of the alloying element in and not create a lot of difficult casting problems because of it. I guess my reputation preceded me a little bit because the program sponsors didn't want to have a difficult to cast alloy. And so the way we started this is we started this with really a pilot program to help understand the castability of the aluminum-cerium alloy system. And it turns out it's really pretty good. The alloy is castable over a broad range of compositions. Not only do we add cerium, which gives us high temperature strength, but we add other alloying elements to improve the room temperature strength as well, and they also improve the high temperature strength when added properly. We've cast over 30 different variations of the alloy. Some have been uncastable. Most have been castable. Some have developed pretty poor mechanical properties. Some have developed quite extraordinary mechanical properties. We'll discuss more, but the alloy is tolerant to really high mag contents. And so people are concerned, well, you're adding cerium, which is a high density material. That is going to make my casting way more. That we can completely counteract that by adding enough cerium to bring the density down to that of pure aluminum. As we see on the bottom left a sandcast kind of hot tear sample. There was a lot of work done to look at feeding ranges, hot tear resistance. We had a lot of resources, including computer-aided tomography, in order to be able to look at what was going on in the alloy and how it varied over various feeding distances. So we had some extraordinary resources that helped us understand these alloys and how to further perfect them. So we've done a bunch of castings. In addition to test bars and test plates and all the normal things that you do in order to validate an alloy, some of the first things we did is cast real castings to see what the die filling capability of the material was. The part in the upper left is a cylinder head for a small engine. We're going to talk about that a little bit later. Is a typical automotive cylinder head for high performance applications. I'm not showing you much of it because we're protecting the identity of the person we're producing it for. In the bottom left is we're looking at very lightweight rotary engines using this alloy, and these are rotors that would potentially go into a rotary engine from this material. And on the lower right, Eck Industries cast a lot of cylinder heads, and they're very difficult to pour and require special handling. And what we did is we poured using the same gating system that we do in 242 alloy, where the heads are normally produced. And we got very, very good results out of that. That right-hand image was the cover image in the, I believe, the July issue of Journal of Materials, where some of the initial work on this alloy was published. So from a casting characteristics, we can say that the binary alloys are as castable as the aluminum silicon alloys. So if I'm doing an aluminum 8% cerium alloy, it has the same castability as an aluminum 8% silicon alloy. And that includes characteristics such as die filling capability, hot tearing resistance, as well as the ability to feed the casting easily. Interestingly, adding magnesium does not really affect the casting characteristics. We've tried some very high magnesium levels in these alloys, and it has been successful. Ironically, for those of us in the foundry business that cast a lot of aluminum silicon alloy, the element that has the biggest negative effect on aluminum cerium alloys from the standpoint of castability is silicon. You're more effective in copper alloys than in silicon alloys, which is interesting, and we're not sure all of the reasons why that's the case, but we've been able to demonstrate it really a number of times. So going into the technical aspects of it, and so we have a curve here, the red curve on my screen, and what we're doing is we're looking at how phases appear and disappear in alloys as the temperature is raised, and you can see that aluminum cerium phase is stable really all the way up to the melting temperature. So nothing is going to happen there. That phase is not going to dissolve or coarsen or do any of those things. The purple is silicon, the silicon phase. Probably more appropriate to look at the mag silicide phase, which would be way over on the left side of the diagram. Here we're looking at the aluminum copper phase, and then the aluminum mag phase in an alloy like 535. So the phase is very, very stable, and that's because of the virtually zero solubility for, it's partially because of the zero solubility of cerium in the mass. And so we have some good-looking microstructures here in the binary aluminum cerium alloys, and a ternary aluminum cerium mag alloy. People ask me about these big phases in here. Well, the phases are not that big. The scale bar is a little different on the aluminum cerium mag. That's a 20 micron scale bar, and the top is as cast, and the bottom is 10 hours of exposure at 540 degrees C. So what you have is, at temperatures that high, you have some homogenization of the aluminum cerium structure, as you do with the magnesium, but the magnesium actually stabilizes that a little bit. So you don't have any growth, you don't have any coarsening, it doesn't disappear, it's still all there after exposure for a long period of time. This is kind of my favorite slide, and it took me a long time to understand it. It comes from Oak Ridge, but it's really trying to understand how the various phases in an alloy accept the stress that's being applied to it. So what you have is in this case, this is a binary picture. So what you have is the pure aluminum here, and this is the aluminum cerium phase here, and then this is what you get in the bulk, and so you get a substantial strengthening because of the, or in the binary alloys, somewhat of a strengthening because of the aluminum-cerium phase. But you know, we're using, in this case, it's 88% aluminum, essentially pure aluminum, and 12% cerium. On the right-hand side, and this is what's interesting. This is an aluminum 12% cerium with 0.4 magnesium. Okay, and so what happens is that the aluminum phase is a little taller, and that's because of the solid solution strengthening that you get out of that little bit of mag that you add. And this phase is much taller. So there's a lot more going on here with the aluminum-cerium phase when you add a little bit of mag. Now we don't completely understand that because there's another phase acting there between either the aluminum-cerium phase and the mag, or the cerium in the mag, which from a calculation standpoint is there, but we haven't really been able to find it in the structure. And that may be because it's nano-sized, or there's some other impact going on that again we just don't understand yet. So here's some mechanical property data. We've been working a lot with the cerium mag system, and in the case of 8 cerium 7 mag, you see some tensile yield and elongation. And then in the case of the aluminum-cerium alloys, this is mechanical properties done at 260 degrees C or 500 degrees Fahrenheit. So at 500 degrees Fahrenheit, we're retaining over 20 KSI tensile in a whole series of alloys here. And we're retaining about 70% of the ultimate tensile strength and about 80% of the yield strength at that temperature. When you compare with other alloys tested at lower temperatures, because there's not a lot of testing work at 260 degrees C for standard alloys, you can see that they have higher, in most cases, higher mechanical properties at room temperature. 201 is still pretty good at 260 degrees C, having a good tensile strength. But alloys like 356 at 210 degrees, they really continue to fall apart. And if you look at the ultimate tensile strength retention, it's only 35% in 356. It's 56% in 201 and about 50% in 518, which is another aluminum mag alloy. So you have very, very stable mechanical properties as you increase, as you add cerium to the alloys, and you improve the room temperature mechanical properties if you add magnesium as just an example element. So there, as I think I said, we did somewhere between 20 and 30 different compositions of alloys using a lot of different alloying elements, and some of these materials responded well to heat treat, and some didn't. I'm going to go back one slide because I will add that these are as-cast properties for the alloy at both room and high temperature for the aluminum-cerium alloys. For the conventional alloys, these are all heat-treated properties. So we're getting very, very good mechanical properties actually without needing to heat treat the alloy. Some compositions were as high as 37 KSI and with yields of 30 KSI after heat treatment. For example, that's the aluminum 12 cerium 4 silicon 0.4 mag. Because of the relatively high silicon level in there, that was actually the alloy with the poorest castability, but it had the best response to heat treat. Some of the binary alloys have no response to heat treat at all. As a matter of fact, mechanical properties. And when I talk about heat treat, I'm talking about a typical type of T6 heat treatment where you're heating it up to 1,000 degrees F and then you're quenching it. So they really don't have much of a response. Once you start adding elements, then you get a lot of response to the heat treat, because you end up with more traditional kind of heat treat response. You get a good response in the cerium nickel series. There's a lot of work that has to be done on heat treat on some of the alloys, particularly that are not primarily magnesium alloys. This is kind of another way of looking at the alloy, how much tensile or yield strength is retained at high temperatures. In this case, it's 260 degrees C, and we're comparing conventional alloys at 210 degrees C, and so you can see there's a lot better retention of properties. You can add cerium in 206, and you get much better retention of properties. Again, you can look. This is this bottom graph is kind of a rehash of the last slide a little bit, but room temperature mechanical properties in a 10 mag alloy, and they're pretty close. Yield strength is higher in 356, but then when we look at high temperature properties, it's very good. And again, the aluminum 8% cerium alloy was not heat treated at all. It was just that's the as-cast properties. We produced the cylinder head casting early on in the program, kind of as a demo project. This was an Oak Ridge National Lab where they 3D printed a carbon fiber car, and they wanted an engine to drive it. And so what they chose is a Honda GX200, a 4-stroke generator engine. And we produced the cylinder head for that in this alloy, and that was all done in rapid prototype as well. This was done in the aluminum-cerium 0.4 mag alloy. And then it was tested. The vehicle was actually driven. There was exhaust gas temperatures of in at least 600 degrees C, and everything went well with the demonstration. There's work going on with our conventional customer base in these alloys in projects of their own that we're looking to participate in. One of the very interesting things, at least to the team, is that when you process these alloys, when you take a typical cast piece of the 8 cerium 10 mag alloy and you extrude it and you align all the aluminum cerium, or at least most of the aluminum cerium, you get very, very high mechanical properties. And again, this is except for the temperature that went into the extrusion billet in order to allow it to extrude. It had tensile strengths in excess of 50 KSI with a 6% elongation in the extruded alloy. So this is a combination of some alloys that are ready to go, some that continue to need development. We are continuing development to improve the room temperature mechanical properties. All of this work was done without making any attempt to do grain refining or modification of the structure. So that's work that's going on right now. We're trying to find optimized heat treat for a number of these alloys. Again, the response in general, because cerium slows the diffusion of almost all the elements involved, we will likely need to heat treat at fairly high temperatures in order to get anything to move. And we're still trying to discover and quantify missing alloy phases that should be there, but we're not seeing, but we know they're there because of the effect they have. We're doing high and room temperature fatigue testing as well as corrosion testing. Although Oak Ridge did some preliminary corrosion testing and it was very, very favorable, so we don't anticipate any problems there. So kind of in summary, these alloys are highly castable, tolerant to casting defects. If you cast any of the binary alloys, the alloys that contain magnesium, you would say that they cast just like 356 does. The combination of your phase constitution, microstructure enables unique mechanical properties, certainly at high temperatures. The aluminum-cerium mag alloys have the best combination of castability, room and high temperature mechanical properties, although we're continuing to work on improving those and looking at other alloying elements that will help improve those. And complex near-net shape castings of aluminum-cerium and aluminum-cerium mag alloys have been produced, and some of them are being evaluated for applications, in particular where operating environments are either steady state at higher temperatures or intermittently at very high temperatures. So for any inquiries, that's my email address, and that's all I have this morning.
Thank you very much, Dave. And thanks to everyone else for sticking along with us. This would be a good time to enter your questions into the question panel in your control panel. And while you guys are doing that, we did have a few come in during the presentation. So David, I'll start you off with this question. Some of the alloys that you discussed have very high levels of magnesium. Doesn't that present a problem with dross formation or difficulty with degassing?
The answer is no. One of the things, you know, we're preparing a paper for Casting Congress coming up in 2017. And we talk more extensively about that. There were a couple things when we did our initial pilot scale production. We produced 700 pounds of the material. And what we did initially is we added the magnesium to alloy it up, and then we added the cerium to the desired level of what we needed. The cerium somehow prevents gas pickup, or reduces it at least, and reduces dross formation. Even in the aluminum 10% mag 8 cerium alloy, we had no more than the usual amount of dross than you would find in any 300 series alloy, and gas pickup that was more typical for 356 alloy as opposed to something like a 535 alloy, which has a fair amount of magnesium in it. So that was really interesting. And when you alloy mag into an aluminum alloy, oftentimes you lose a percentage of that mag, which we did when we did our initial alloying. But when we came back the next morning, we had lost almost none of it. So something is going on with the magnesium and cerium. That's, I'm going to say, a good thing for the foundry that we haven't completely figured out yet.
Okay, thank you. Another question is, with which cerium alloy is furthest along in development and research, and what applications are showing the most promise?
The alloy that is furthest along, that we've done the most extensive testing on, is the 8 cerium 10 magnesium alloy. It is being evaluated in in a number of components now, including a number of different classes of cylinder heads, where people are looking for high temperature, a better high temperature performance of the material, and that is the alloy that we continue to primarily work on and characterize. These alloys, we're preparing the documentation to get a number from the Aluminum Association, since the alloys are for sale, we expect that that'll be the first one that'll be fully commercialized. But we split our research time optimizing that alloy and continuing to look at new alloy combinations.
All right, thank you. Next was a question about if these alloys would be suitable for metal powder 3D printing. I don't know if you've done much looking into that.
Well, we have. Actually, we are. We believe that they will be. There's no fundamental reason that they are not. We have had a couple of inquiries relative to that. We're still looking for a partner to work with. We've got plenty of alloy that can be converted into powder to see how it works. The other thing that is, now that you mentioned 3D printing, the other thing that is very interesting about these alloys, they have kind of a unique rheology that makes people believe that it's possible to wire feed these alloys in kind of a 3D printer application. It's a little bit more speculative, but there's the possibility that can be done as well.
Great, thank you. Next, what is the minimum wall thickness anticipated being able to cast in larger complex castings?
That's one of those big open-ended questions. The answer is it's the same as the wall thickness that you would define in 356 for a large complicated casting. The die filling ability seems to be equivalent in these alloys. You could probably go thinner than 356 if you stuck with the binary compositions. At a 10% or 9.5% cerium right near the eutectic, the fluidity is just extraordinary. But the mechanical properties are not that great with just the binary. But in general, they're going to be about the same as in 356.
Okay, we had a couple questions that are cerium related, so I'll just ask those together. One was, does the cerium attack the furnace refractory? And then the other one was there any cerium contamination with other alloys in the foundry? Can you tell if there's anything else going on with related to cerium?
Okay, both good questions. We have done all of the work at this point in a couple different furnaces. One, the alloy development work in a small furnace at 30 kilograms or something, and one in a larger melting crucible at 350 kilograms. We've done enough melting to speculate that there's no unusual cerium attack that goes on. that has not been tested with other refractories yet, but I think that would be fairly simple to do. The alloy itself is, seems to be fairly non-reactive. We're getting no unusual reactions with mold wash in permanent molds or core washes in sand or core binder system. So it seems very stable, although we haven't taken it all the way through. We are working on recycling studies currently in answer to the other question. There are some that have asked what happens if this material gets into the scrap stream in a big way. And so what we're doing is we're looking at contaminating 356, 535, and 206 with cerium levels up to about 1%. They're actually going to be at 0.1, 0.5, and 1%. To understand what the impact of mechanical properties are, if you accidentally contaminate, we don't know. We don't know that 0.1% cerium won't actually improve those alloys. There's not enough literature out there to support the question one way or the other. To be safe, right now we're working in dedicated furnaces, and we'll have that answer in a few months, actually.
Okay, great. I think we have time for 2 or 3 more questions. So the next couple, what casting processes have you tried with the alloy, and were the samples cast in or extruded through graphite or steel dies?
Okay, for the test bars in general were permanent mold test bars, standard ASTM test bars. The test plates and hot tear molds were done in sand casting. We have the production castings that we've run. We have run a bunch of production castings in standard tilt pour permanent molds. We've done green sand. We have done chemically bonded sand. There is some, like almost any other aluminum alloy, there will be some effect on cooling rate and solidification rate in these alloys, but it doesn't seem to be as drastic as in some alloys like 206. So the mechanical properties that I reported are unchilled mechanical properties in either sand or permanent mold, and you can get slightly higher properties if you use chills. But kind of the whole thing with chilling and thermal gradients works the same in this alloy as it does like an alloy with like 356.
Okay, last question.
We didn't use any graphite, by the way.
Okay, thanks. Well, one last question, and let's see, what is the alloy cost compared to the 242 alloy?
So the last time we priced the alloy, and I'm not sure exactly what 242 is today, but if I were to price in production volumes an aluminum 10% magnesium 8% cerium alloy, cost would be about $1.75 a pound. I think that's probably a little higher than 242 is at the time. It kind of depends upon the commodity prices, but this is, and what that goes to as more and more of this is used and produced, I think it'll go no place but down. It's you know, it's not, certainly not a $5 and $10 alloy. It is an alloy that fits, I think, squarely into the normal range of prices for premium aluminum alloys.
All right. Well, thank you very much, David, and thank you to all who attended. If you have any additional questions, I say please do touch base with David at his email address there. But thanks again, David.
Okay. Thank you very much.
Take care,
Bye.
all.